failure mode and effects analysis was one of the first systematic techniques for failure analysis. It was developed by reliability engineers in the 1950s to study problems that might arise from malfunctions of military systems. An FMEA is often the first step of a system reliability study. It involves reviewing as many components, assemblies, and subsystems as possible to identify failure modes, and their causes and effects. For each component, the failure modes and their resulting effects on the rest of the system are recorded in a specific FMEA worksheet. There are numerous variations of such worksheets. An FMEA is mainly a qualitative analysis. A few different types of FMEA analyses exist, such as functional, design, and process FMEA. Sometimes FMEA is extended to FMECA to indicate that criticality analysis is performed too. FMEA is an inductive reasoning single point of failure analysis and is a core task in reliability engineering, safety engineering and quality engineering. Quality engineering is specially concerned with the process type of FMEA. A successful FMEA activity helps to identify potential failure modes based on experience with similar products and processes, or based on common physics of failure logic. It is widely used in development and manufacturing industries in various phases of the product lifecycle. Effects analysis refers to studying the consequences of those failures on different system levels. Functional analyses are needed as an input to determine correct failure modes at all system levels, both for functional FMEA or piece part FMEA. An FMEA is used to structure mitigation for risk reduction based on either failure effect severity reduction or based on lowering the probability of failure or both. The FMEA is in principle a full inductive analysis, however the failure probability can only be estimated or reduced by understanding the failure mechanism. Ideally this probability shall be lowered to impossible to occur by eliminating the causes. It is therefore important to include in the FMEA an appropriate depth of information on the causes of failure. Introduction. The FMEA is a design tool used to systematically analyze postulated component failures and identify the resultant effects on system operations. The analysis is sometimes characterized as consisting of two sub-analyses, the first being the failure modes and effects analysis, and the second, the criticality analysis. Successful development of an FMEA requires that the analyst include all significant failure modes for each contributing element or part in the system. FMEAs can be performed at the system, subsystem, assembly, subassembly or part level. The FMECA should be a living document during development of a hardware design. It should be scheduled and completed concurrently with the design. If completed in a timely manner, the FMECA can help guide design decisions. The usefulness of the FMECA as a design tool and in the decision-making process is dependent on the effectiveness and timeliness with which design problems are identified. Timeliness is probably the most important consideration. In the extreme case, the FMECA would be of little value to the design decision process if the analysis is performed after the hardware is built. While the FMECA identifies all part failure modes, its primary benefit is the early identification of all critical and catastrophic subsystem or system failure modes so they can be eliminated or minimized through design modification at the earliest point in the development effort. Therefore, the FMECA should be performed at the system level as soon as preliminary design information is available and extended to the lower levels as the detailed design progresses. Remark: for more complete scenario modeling another type of reliability analysis may be considered, for example fault tree analysis, FTA. A deductive failure analysis that may handle multiple failures within the item and/or external to the item including maintenance and logistics. It starts at higher functional/system level. An FTA may use the basic failure mode FMEA records or an effect summary as one of its inputs. Interface hazard analysis, human error analysis and others may be added for completion in scenario modeling. Functional analysis: the analysis may be performed at the functional level until the design has matured sufficiently to identify specific hardware that will perform the functions. then the analysis should be extended to the hardware level. When performing the hardware-level Fmea, interfacing hardware is considered to be operating within specification. In addition, each part failure postulated is considered to be the only failure in the system. In addition to the FMEAs done on systems to evaluate the impact lower-level failures have on system operation, several other FMEAs are done. Special attention is paid to interfaces between systems and in fact at all functional interfaces. The purpose of these FMEAs is to assure that irreversible physical and/or functional damage is not propagated across the interface as a result of failures in one of the interfacing units. These analyses are done to the piece part level for the circuits that directly interface with the other units. The FMEA can be accomplished without a CA, but a CA requires that the FMEA has previously identified system-level critical failures. When both steps are done, the total process is called a FMECA. Ground rules. The ground rules of each FMEA include a set of project-selected procedures. The assumptions on which the analysis is based. The hardware that has been included and excluded from the analysis and the rationale for the exclusions. The ground rules also describe the indenture level of the analysis, the basic hardware status, and the criteria for system and mission success. Every effort should be made to define all ground rules before the FMEA begins. However, the ground rules may be expanded and clarified as the analysis proceeds. A typical set of ground rules follows: only one failure mode exists at a time. All inputs to the item being analyzed are present and at nominal values. All consumables are present in sufficient quantities. Nominal power is available. Benefits. Major benefits derived from a properly implemented FMECA effort are as follows. It provides a documented method for selecting a design with a high probability of successful operation and safety. A documented uniform method of assessing potential failure mechanisms, failure modes and their impact on system operation, resulting in a list of failure modes ranked according to the seriousness of their system impact and likelihood of occurrence. Early identification of single failure points and system interface problems, which may be critical to mission success and/or safety. They also provide a method of verifying that switching between redundant elements is not jeopardized by postulated single failures. An effective method for evaluating the effect of proposed changes to the design and/or operational procedures on mission success and safety. A basis for in-flight troubleshooting procedures and for locating performance monitoring and fault detection devices. Criteria for early planning of tests. From the above list, early identifications of SFPS, input to the troubleshooting procedure and locating of performance monitoring/fault detection devices are probably the most important benefits of the FMECA. In addition, the FMECA procedures are straightforward and allow orderly evaluation of the design. Basic terms. The following covers some basic FMEA terminology. Failure, the loss of a function under stated conditions. Failure mode, the specific manner or way by which a failure occurs in terms of failure of the item's system, function under investigation. It may generally describe the way the failure occurs. It shall at least clearly describe a failure state of the item under consideration. It is the result of the failure mechanism. For example, a fully fractured axle, a deformed axle or a fully open or fully closed electrical contact are each a separate failure mode. Failure cause and/or mechanism, defects in requirements, design, process, quality control, handling or part application, which are the underlying cause or sequence of causes that initiate a process that leads to a failure mode over a certain time. A failure mode may have more causes. For example, fatigue or corrosion of a structural beam, or fretting corrosion in an electrical contact is a failure mechanism and in itself not a failure mode. The related failure mode is a full fracture of structural beam, or an open electrical contact. The initial cause might have been improper application of corrosion protection layer, and/or abnormal vibration input from another system. Failure effect, immediate consequences of a failure on operation, function or functionality, or status of some item. Indenture levels, an identifier for system level and thereby item complexity. Complexity increases as levels are closer to 1. Local effect, the failure effect as it applies to the item under analysis. Next higher level effect, the failure effect as it applies at the next higher indenture level. End effect, the failure effect at the highest indenture level or total system. Detection, the means of detection of the failure mode by maintainer, operator or built-in detection system, including estimated dormancy period, risk priority number, cost probability detection, severity, the consequences of a failure mode. Severity considers the worst potential consequence of a failure, determined by the degree of injury, property damage, system damage and/or time lost to repair the failure. Remarks/mitigation/actions, additional info, including the proposed mitigation or actions used to lower a risk or justify a risk level or scenario. History. Procedures for conducting FMEA were described in U.S. Armed Forces Military Procedures Document MILP 1629. Revised in 1980 as MILSTD 1629A. By the early 1960s, contractors for the U.S. National Aeronautics and Space Administration were using variations of FMEA or FMEA under a variety of names. NASA programs using FMEA variants included Apollo, Viking, Voyager, Magellan, Galileo, and Skylab. The civil aviation industry was an early adopter of FMEA, with the Society for Automotive Engineers publishing ARP 926 in 1967. After 2 revisions, ARP 926 has been replaced by ARP 4761, which is now broadly used in civil aviation. During the 1970s, use of FMEA and related techniques spread to other industries. In 1971 NASA prepared a report for the U.S. Geological Survey recommending the use of FMEA in assessment of offshore petroleum exploration. A 1973 U.S. Environmental Protection Agency report described the application of FMEA to wastewater treatment plants. FMEA's application for HACCP on the Apollo space program moved into the food industry in general. The automotive industry began to use FMEA by the mid-1970s. The Ford Motor Company introduced FMEA to the automotive industry for safety and regulatory consideration after the Pinto affair. Ford applied the same approach to processes to consider potential process-induced failures prior to launching production. In 1993 the Automotive Industry Action Group first published an FMEA standard for the automotive industry. It is now in its 4th edition. The SA first published related standard J1739 in 1994. This standard is also now in its 4th edition. Although initially developed by the military, FMEA methodology is now extensively used in a variety of industries including semiconductor processing, food service, plastics, software, and healthcare. Toyota has taken this one step further with its design review based on failure mode approach. The method is now supported by the American Society for Quality, which provides detailed guides on applying the method. The standard failure modes and effects analysis and failure modes, effects and criticality analysis procedures, however, do not identify the product failure mechanisms and models, which limits their applicability to provide a meaningful input to critical procedures such as virtual qualification, root cause analysis, accelerated test programs, and to remaining life assessment. To overcome the shortcomings of FMEA and FMECA of failure modes, mechanisms and effect analysis has often been used. Example worksheet, design FMEA, probability. It is necessary to look at the cause of a failure mode and the likelihood of occurrence. This can be done by analysis, calculations/FEM, looking at similar items or processes and the failure modes that have been documented for them in the past. A failure cause is looked upon as a design weakness. All the potential causes for a failure mode should be identified and documented. This should be in technical terms. Examples of causes are human errors in handling, manufacturing-induced faults, fatigue, creep, abrasive wear, erroneous algorithms, excessive voltage or improper operating conditions or use. A failure mode is given a probability ranking. Severity, Determine the severity for the worst-case scenario adverse end effect. It is convenient to write these effects down in terms of what the user might see or experience in terms of functional failures. Examples of these end effects are, full loss of function X, degraded performance, functions in reversed mode too late functioning, erratic functioning, etc. Each end effect is given a severity number from, say, I to 6, based on cost and/or loss of life or quality of life. These numbers prioritize the failure modes. Below a typical classification is given. Other classifications are possible. See also hazard analysis. Detection, the means or method by which a failure is detected, isolated by operator and/or maintainer and the time it may take. This is important for maintainability control and it is especially important for multiple failure scenarios. This may involve dormant failure modes or latent failures. It should be made clear how the failure mode or cause can be discovered by an operator under normal system operation or if it can be discovered by the maintenance crew by some diagnostic action or automatic built-in system test. A dormancy and/or latency period may be entered. Dormancy or latency period. The average time that a failure mode may be undetected may be entered if known. For example, during aircraft C block inspection, preventive or predictive maintenance, X months or X flight hours, during aircraft B block inspection, preventive or predictive maintenance, X months or X flight hours, during turnaround inspection before or after flight, during in-built system functional test, X minutes, continuously monitored, X seconds. Indication, if the undetected failure allows the system to remain in a safe/working state, a second failure situation should be explored to determine whether or not an indication will be evident to all operators and what corrective action they may or should take. Indications to the operator should be described as follows: normal. An indication that is evident to an operator when the system or equipment is operating normally. Abnormal. An indication that is evident to an operator when the system has malfunctioned or failed. Incorrect. An erroneous indication to an operator due to the malfunction or failure of an indicator. Perform detection coverage analysis for test processes and monitoring. This type of analysis is useful to determine how effective various test processes are at the detection of latent and dormant faults. The method used to accomplish this involves an examination of the applicable failure modes to determine whether or not their effects are detected, and to determine the percentage of failure rate applicable to the failure modes which are detected. The possibility that the detection means may itself fail latent should be accounted for in the coverage analysis as a limiting factor. Inclusion of the detection coverage in the Fmea can lead to each individual failure that would have been one effect category now being a separate effect category due to the detection coverage possibilities. Another way to include detection coverage is for the FTA to conservatively assume that no holes in coverage due to latent failure in the detection method affect detection of all failures assigned to the failure effect category of concern. The Fmea can be revised as necessary for those cases where this conservative assumption does not allow the top event probability requirements to be met. After these three basic steps, the risk level may be provided. A micron risk level and risk is the combination of end effect probability and severity, where probability and severity includes the effect on non-detectability. This may influence the end effect probability of failure or the worst case effect severity. The exact calculation may not be easy in all cases, such as those where multiple scenarios are possible and detectability/dormancy plays a crucial role. In that case, fault tree analysis and/or event trees may be needed to determine exact probability and risk levels. Preliminary risk levels can be selected based on a risk matrix like shown below, based on MIL. STD 882. The higher the risk level, the more justification and mitigation is needed to provide evidence and lower the risk to an acceptable level. High risk should be indicated to higher level management, who are responsible for final decision-making. After this step, the Fmea has become like a Fmeca. Timing: the Fmea should be updated whenever a new cycle begins, changes are made to the operating conditions, a change is made in the design, new regulations are instituted, Customer feedback indicates a problem. Uses, development of system requirements that minimize the likelihood of failures. Development of designs and test systems to ensure that the failures have been eliminated or the risk is reduced to acceptable level. Development and evaluation of diagnostic systems, to help with design choices. Advantages, improve the quality, reliability and safety of a product process, improve company image and competitiveness, increase user satisfaction, reduce system development time and cost, collect information to reduce future failures, capture engineering knowledge, reduce the potential for warranty concerns, early identification and elimination of potential failure modes, emphasize problem prevention, minimize late changes and associated cost, catalyst for teamwork and idea exchange between functions, reduce the possibility of same kind of failure in future, reduce impact on company profit margin, improve production yield. Limitations. While Fmea identifies important hazards in a system, its results may not be comprehensive and the approach has limitations. In the healthcare context, Fmea and other risk assessment methods, including swift and retrospective approaches, have been found to have limited validity when used in isolation. Challenges around scoping and organizational boundaries appear to be a major factor in this lack of validity. If used as a top-down tool, Fmea may only identify major failure modes in a system. Fault tree analysis is better suited for top-down analysis. When used as a bottom-up tool, Fmea can augment or complement FTA and identify many more causes and failure modes resulting in top-level symptoms. It is not able to discover complex failure modes involving multiple failures within a subsystem, or to report expected failure intervals of particular failure modes up to the upper-level subsystem or system. Additionally, the multiplication of the severity, occurrence and detection rankings may result in rank reversals, where a less serious failure mode receives a higher RPN than a more serious failure mode. The reason for this is that the rankings are ordinal scale numbers, and multiplication is not defined for ordinal numbers. The ordinal rankings only say that one ranking is better or worse than another, but not by how much. For instance, a ranking of 2 may not be twice as severe as a ranking of 1, or an 8 may not be twice as severe as a 4, but multiplication treats them as though they are. See level of measurement for further discussion. Types, functional. Before design solutions are provided, functions can be evaluated on potential functional failure effects. General mitigations can be proposed to limit consequence of functional failures or limit the probability of occurrence in this early development. It is based on a functional breakdown of a system. This type may also be used for software evaluation. Concept design/hardware. Analysis of systems or subsystems in the early design concept stages to analyze the failure mechanisms and lower-level functional failures, especially to different concept solutions in more detail. It may be used in trade-off studies. Detailed design/hardware, analysis of products prior to production. These are the most detailed FMEAs and used to identify any possible hardware failure mode up to the lowest part level. It should be based on hardware breakdown. Any failure effect severity, failure prevention, failure detection and diagnostics may be fully analyzed in this FMEA. Process, analysis of manufacturing and assembly processes. Both quality and reliability may be affected from process faults. The input for this FMEA is amongst others a work process/task breakdown. See also, references.